Well, now we have a terrific sponsor talk coming up from Avicenna. Avicenna is an amazing pioneer in actually an area that Peter Vincer talked about yesterday for Nubis Communications of going to surface mount vertical clusters of optical I/O to solve the shoreline problem. And Avicen has a unique way of doing that. Dr. Chris Pfistner is head of sales and marketing at Avicenna. I don't think I've ever met a company that had more PhDs in top positions from technical program managers, CTO, sales, marketing, and uh, and even operations. Um, so it's just a pleasure to introduce Chris. I've known him for quite some time, and as a sales and marketing guy, this guy is a deep technologist as well. So, Chris, the floor is yours.
Well, thank you, Dan. Thank you for the warm welcome. I assume everyone can hear me. I'd also like Deepak for setting the stage here for us, kicking us off with a terrific keynote this morning. I'm going to share my slide. See, I should have presentation mode now. I'm going to turn on a laser pointer here.
There you go.
Are we good?
We are good.
Okay. Yeah, so we're going to talk about this, as Dan pointed out, paradigm shift in AI clusters, and this is now using microLED based interconnects, specifically aimed at scale up. I'm going to set the stage, but this is our version. There's many versions of these. It's basically these days in AI networks, it's all about energy efficiency because data centers are projected to possibly exceed 20% of global energy usage by 2030. And the other, this is one representation of it. The other fact of life is that the process capacity has outstripped the interconnect capacity, and we're in need of a new technology to cope with that. In the data center architectures, that's where AI, most of AI calculations are happening these days. Basically, have three categories of interconnects. We have the transport networks; those have been optical for a long time. Intra data center, we have scale out, and optics has pretty much taken over this. So this is linking racks. These are traditional transceivers. NVIDIA is now proposing to introduce co-packaged optics for this starting later this year. We'll see. We're all looking forward to that. But the scale up portion of the network, so that's basically scaling the size of the individual computer clusters, that is still done in copper, and it's rapidly coming to an end. Here is a picture of the NVIDIA flagship, the NVL72. And you can see in the backplane, this is a massive cluster of DAC cables, over 5,000 per rack, but they're all limited basically to 1 meter reach. So what's happening is a lot of talk about how do we get past that limit? How do we start to expand from one rack to multiple racks? There was a terrific workshop hosted by NVIDIA, not surprisingly, at OFC, where they summarized sort of 5 key aspects of what's needed in terms of parameters, energy efficiency, much below the 5 picojoules that are considered kind of the sound barrier currently for optical links. Shoreline density, a terabit or better per millimeter. Reach doesn't really need to be more than 10 meters. We now see there's another version of this coming up, and that's out of OIF. They're proposing to extend that to 20 meters. High reliability, higher than other optical links. And of course, the cost target, it can't be in the range of current optical links. I'm just gonna flash up how this would stack up with LED links. Energy efficiency, we can definitely achieve picojoule per bit or less. We can match the necessary bandwidth density because we're dealing with 2D arrays. We can extend the reach to 20 meter as needed. And in terms of fit rates, well, we don't have those new links are not deployed in large numbers yet. That's what will be needed to get a final fit number. But we're off to a good start with gallium nitride LEDs because they're generally very reliable. They're very temperature tolerant. We can easily do a mil-spec range. We've actually shown a demonstration with our partner, University of North Carolina. They showed it operating all the way to 400 degrees C. So lots of other things need to come into place for that. And they're very cost effective, again, because it's a technology that's getting optimized by micro display. The micro display and the whole ecosystem that goes with it, and those use millions of LEDs. We only need a few hundred typically per cluster. So how does the whole thing look? It's a modular architecture. You can see in the top right here, you basically use a cluster of LEDs. We're showing 2 clusters here, depending on how you architect it. On a typically like a kind of 12 nanometer process node. Next to it, you have the PDs. So those are your 2 transmit and receive front-end chips, if you like. Vertical emission through a lens array, going through your fiber coupler, the transport by fiber, and then terminate on the other side on the LEDs. Depending on what architecture you use, if you use high-speed SerDes, because fact of life, today all scale-up networks still run in 200 gigabit per lane. So that is an architecture that the ecosystem has chosen. In that case, you'll have a high-speed SerDes here that will add an energy tax, but that's basically temporary. Out here, you have a die-to-die interface. And then what you can do with this architecture is you can use it on board, so outside of the package, because once you go inside the package, which is definitely an architecture that we're also pursuing, that will be co-packaged, but that's a much bigger effort in terms of collaboration with your processor design entity. Few more words on how the technology works. By the way, at 2 p.m. this afternoon, our founder and CEO, Bardia Brzezski, he'll give a talk where he dive much deeper into the technology. I'm going to focus more on the applications in this talk here. But what we do is the LEDs, they're grown on sapphire, gallium nitride. They're then flip chip transferred using processes that have been developed for the micro display industry. Transferred onto CMOS, can be transferred onto any CMOS node. You focus, so this is what the LED array looks like. You focus through a lens array. These look like these egg holders here. That's the array that you see here. Couples into the fiber, transports across, comes out on the other side, gets again focused, passes through a micro lens array, and then gets terminated on PDs. Since we're operating in the blue, like 425 nanometer, silicon is actually an excellent detector. You have an absorption length of less than a micron, so this is there's no exotic materials needed. So this thing is geared for simplicity and low cost. For those who like to think in terms of diagrams, this is a diagram that was originally generated by DARPA, but it compares different interconnect types using the reach across the bottom. Here is 1 meter. As you can see to the right, as you're going out, optical has always dominated. And for shorter reaches, copper has always dominated and still does. And what you have on the y-axis is a figure of merit. It consists of bandwidth density. How much bandwidth can you get out of a millimeter of shoreline in a chip? And then energy efficiency. That's a big topic. This is expressed in picojoule per bit. And so we're talking energy efficiency. So the bigger this figure of merit, the better your interconnect. And basically here at this level, take this copper interface, HBM, that we know today goes roughly over a millimeter distance from a processor to an HBM stack. As you can tell, the microLEDs can extend that efficiency out to about 10 meters. If you need to go further distance, other technologies are better suited. Those are all laser-based, and they all have higher energy consumption or lower efficiency. But that's the kind of the sweet spot, and that's exactly the sweet spot that we are looking at for scale-up. What do we do with this technology? We are coming out with a full demo kit later this year. The first product, while not the ideal application, but it is something that can still benefit from the energy efficiency, is basically package it into an AOC, or what's now coming up. A lot of different entities are proposing high-density pluggable connectors because, as was pointed out by Microsoft in the previous talk, we're looking at interconnects starting around 6.4 terabits, but rapidly scaling to doubling that to 12.8, and then probably doubling that again to 25 terabits. And of course, this is more or less a copy exact of the 1.6 tera tiles, if you like. This is still all outside of the package. The vision remains to go inside the package, eventually be right on the interposer, what a lot of people refer to as CPO. And what we're also getting now, and that's a little further out, that's more in the 2030 timeframe, we're getting a lot of interest in optical memory interconnects. And one driver has become these GPUs, next generation GPUs. People are projecting up to 2000 watt power consumption. So you need to get the memory away from the hot source. So that's what's driving this. This is not so much about memory pooling. That's another architecture that's also in discussion. But this is really just getting memory outside the package and spreading it out, also make it accessible for a larger memory bank. Just a couple of words. Again, there will be a talk this afternoon, but in latest technical achievements, while the current incarnation of LEDs run at 4G per lane, we've already shown 16 per lane performance now in our labs. And we've also, partnering with TSMC on the detectors, we've also shown ultra-low power links because you get much more efficient, better responsivity on your detectors. You can then dial back the power on the transmitter. So we've achieved a 0.2 picojoule bit per link. As you can see here, this is an individual link, and still the bit error rate of a little better than 10 to the minus 7. With this, I'll summarize. I know I'm coming up on the end point here. Micro-LED interconnects, they're really well suited for scale-up networks because of their energy efficiency, their shoreline density, think a terabit per millimeter, the reach 10 to 20 meters. So this is a sweet spot. If you need long distance, this is not the optical technology, but the 10 to 20 is really in the sweet spot for scale-up. And the operating temperature is very wide. Now in data centers, that's usually not an issue for ambient temperature, but with hot running processors, you do actually, a lot of these processors run beyond 100 degrees Celsius. So it is definitely good to know that we're covered on that front. With this, I'll turn it over to Dan again, and thank you very much for your attention.
Thank you, Chris. Fascinating developments, and they continue to move along quickly. We would love to have your slides available. Again, if you could remove the confidential markings, then people won't feel conflicted about downloading them. So thank you, Avicenna.